Okay, good morning, everybody. Where we left off last time, we were talking about binomial distributions. And of course, that's when you have n independent trials. For each trial, the probability of success is the same, and there are only two outcomes for each trial, like success or failure. So today, that was in section 6.3. We're going to go back and pick up some things from section 6.1 and 6.2 today. And what we're leaning towards, by the time we finish this, you'll see how we can approximate binomial distributions by normal distributions. And then we're going to go ahead after that, and the focus of this whole second rotation will be based on sampling. You want to make predictions for the population. So for example, you sample 50 people, and 35% of the sample vote one way. You wonder, well, I wonder what it is for the whole population. And we're going to do that, and we're going to do hypothesis testing. But the focus for today, again, let's go back to pick up some things from section 6.1, 6.2. So I'm going to share my paper with you. Okay. So I just made some notes here to save some time. I think we talked about some of these things before, but I'll mention them again. The discrete versus continuous random variables. So again, a discrete means you can only take on usually like a finite number of values, versus continuous can take on infinitely many values, or typically like some values all within an interval. So for example, say you want to flip a coin 3 times and X is the number of heads you can get. Well, X can either be 0, 1, 2, or 3. So that's discrete. Okay, you only have 4 possibilities. However, if you talk about your height rounded off, like say to the nearest whole number, that's discrete. Maybe your height's 50 inches, 51, 52, or up to 80 inches. So that's discrete. Now, temperature rounded off would be discrete. However, if you take temperature that's not rounded off, you could have, say, a temperature anywhere between 50 degrees and 70 degrees, but that could include many, 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 many decimal places, or your height not rounded off. Okay, say your height's between 49.3 and 84.2 inches. Okay, some examples we saw of continuous functions are like normal distributions are continuous functions, versus when we looked at binomial distributions, say you flip a coin, as we set up here, 3 times, that'd be X is the number of heads. That's a binomial distribution. When we did that, we had like a bar chart for it. Now, what we're going to see is eventually, like the more times you flip a coin, and the coin isn't too biased, your distribution, that bar chart, is going to look more and more like a normal distribution. Okay, now let's go back to some formulas we saw before. So we had a formula for X bar, which is basically, so again, this notation, the summation notation, is if I have a frequency table, it's your Xi times your frequency, and then that's divided by the total of all the frequencies. So for example, say you have these numbers here. You see that the 2 is there 3 times, the 3 is there 5 times, the 4 is there 2 times, and the total of the frequencies here is 3 plus 5 plus 2. There are 10 numbers altogether. Okay, get the total here, get 2.9. Okay, now another way we can look at this is since each time we are dividing by 10 here, we can write this as the summation of Xi times frequency divided by 10. And when you do this, this is called the relative frequency. And this relative frequency looks sort of like a probability. So we get the same answer here, but I'm just going to write this slightly different as xi times pi, where pi is like a probability. Okay, now the reason why I want to do that is because we're going to kind of generalize this formula. And if you know what the probabilities are, like instead of just doing an experiment, but you know what the probabilities are, then we're going to call this expression here mu instead of x bar. So you pronounce it mu, Greek letter, which is also the expected value of x, okay, which is this formula. So here's an example. Say you want to flip a biased coin 3 times, and the probability of heads each time is 0.3. Let x equal the number of heads. Okay, so x can be either 0, 1, 2, or 3. So you remember the formulas we had from last time to calculate binomial probabilities, which looks like this. NCR p to the r power times 1 minus p to the n minus r power. And as I'm talking through this, instead of 1 minus p, I might refer to this as q. So these are our numbers here. And I make this is called a probability distribution table. I have the values of x here. I have the probabilities here. So if I use this formula, 0 times 0.343 plus 1 times 0.441 and so forth, I get 0.9. Okay, so this is called the expected value, which is mu. And this, what this means is on average, if you flip this biased coin 3 times, on average, you would expect to get 0.9 heads. Okay, now of course you can't get 0.9 heads if you flip it 1 time, but this is over and over and over again. All these trials you do it, you average out how many heads you get, and that's the average you would get theoretically. You can try this at home when you get bored. Try flipping a coin three times, okay? See how many heads you get. Well, you need a bias coin though. And do it 1,000 times. Take the average, that's what you get, okay? If we were actually at school, we would have time to do things, probably with a regular coin, not a bias coin. All right. We also had a formula for standard deviation before. Well, this is the variance here. The variance is that we had the sum, we had x high minus x bar, whole thing squared over n, where n is the sum of all the frequencies. Okay, and again, this fi divided by the n here, I call that a pi, p sub I, that's not pi, that's p sub I, which is a relative frequency. Okay, now again, if you're doing it theoretically, instead of using x bar here, the theoretical mean is mu, so I get this formula. Summation xi minus mu squared times p sub I. So that's the formula for, this is actually population variance. And this is population standard deviation. Okay, so for the previous coin problem we had, if I want to use this formula here, I took the, there we go, the x value here, minus the mean, which we got was 0.9 squared, times the probability, the probabilities here, okay? So you can see the next one would be 1 minus 0.9 squared times the probability, plus 2 minus 0.9 squared times the probability, plus 3 minus 0.9 squared times the probability, okay? We add those up, and we get 0.63 is the variance. So this is your sigma squared. And to get sigma, we take the square root of that. Okay, now you can do this on your calculator. List 1, I put my value 0, 1, 2, 3. List 2, I put my 4 probabilities. Okay, on your calculator, you can do stat, then calculate, then do one variable stat. Now this is important. You have list 1, comma, list 2 on the older calculators like mine, or else on the newer calculators, they might say, what's your list and what's your frequency list? And you put L2 in there. Okay, the printout will look like this. It will say X bar equals 0.9, but this X bar is actually the mu is 0.9. And you go to find the sigma, and that will give you 0.7937, the same as this. Notice they don't give you the variance on there, which is kind of strange. I don't know why, but they do give you the sigma. So try this out on your calculator. You'll turn the video off for a second. Try this out. Make sure you can get that. Okay, next. Oh, this is just as an aside here. Just as this, if you've had calculus before, if you had, especially if you had BC calculus, for a continuous random variable, the probability is given by the area under the density curve. So, for example, if you have a normal curve like this, there's actually an equation for this, okay? So this is the equation for this curve, all right? So to get the area underneath here, say you want, this is like a z here instead of an x. If you want the probability that z is between 1 and 2, you take the integral from 1 to 2 of this. From BC calculus, you don't know how to integrate this. We don't have techniques for that. But you can do the f and int on your calculator. So you can try that just for fun. Like Keenan, I know you're going to try this. Just for fun, do the f and int on your calculator. Do this. And then look on your calculator and look at normal CDF. Okay. From 1 to 2. Okay. And if your calculator requires it, for the mean is 0, standard deviation is 1. That should give you the same thing. So let's try it. This is just if you had calculus. Otherwise, don't worry about it. It's not necessary. Okay, a little bit review of some things we did before when we were combining random variables. We saw before that if y equals ax plus b, where x is a random variable, we had y bar was ax bar plus b. Okay. So let me give you an example. Say we have x bar is 5, and say we have sigma x is 2, and we had like y equals 3x plus 7. Okay, what we saw before, if you want to get y bar, we just take 3 times x bar plus 7. So we get 3 times 5 plus 7, which is 22. We had that sigma y is, notice the 7 didn't affect it at all, but the 3 does. So S of y is 3 times S of x. So S of y would be 3 times 2, which is 6. And to get the variance, we take the standard deviation squared. So that was actually 3 squared. Times the variance. The variance would be 2 squared. Okay. So that's what we did before. So again, if we're doing it more theoretically, the notes here, this was important, right? A could be a negative number. but since standard deviation is always positive, we have the absolute value of A in there. Okay, so theoretically, we're going to have, if y equals ax plus b, mu sub y equals a times mu sub x plus b. Variance of y, sigma squared y, is a squared times the variance for x. And sigma y is the absolute value of a times sigma of x. So these are exactly the same formulas, just instead of an x bar, you have a mu in there. And instead of an s, you have a sigma in there. Okay. Okay. Some other formulas we had. Well, then let me do the same example I had up here. Say we have another variable w. Say we have w bar was 3, and SW, say, is 1, okay? So if I take these two variables and add them together, x plus w, okay? Let's call this S for sum, okay? Then we saw before, if you take the S bar, that gives you x bar plus w bar, which is 5 plus 3, which is 8, okay? So this is just using the mu notation there. So the expected value of x plus y, or mu of x plus y, is just mu of x plus mu of y. Same thing if you take the difference, you have a subtraction here. Now we had this other property, and this was important. We said if x and y are independent variables, then to get the variance of x plus y, or the variance of x minus y, that equals the variance of x plus the variance of y. It's always a plus sign, okay? Which is sigma squared x plus sigma squared y. So if you want to get sigma of x plus y, we have to take the square root of the variance, okay? So this is important. Sigma x plus y does not equal sigma x plus sigma y, okay? No. So remember this formula. I think it's on the formula sheet. Here's an example. So let's suppose in country X, the mean weight is 153, standard deviation 17. Country Y, the mean weight is 165, standard deviation is 25. Suppose X and Y are both normally distributed and they are independent. Okay, now one property I think we talked about, but we're not going to prove it. If two variables are normally distributed, then the sum of the two variables will also be normally distributed, but we're not going to prove that. Okay, so let's say one person from country X and one person from country Y are selected at random. Okay, so I want to find what's the probability that the sum of their heights, sum of their weights, sorry, is more than 300. Okay, so I want to, since I said the sum of two normal variables will be normal, I want to change this into a z-score. Okay, so I need to find the mean of x plus y and the standard deviation for x plus y. So I'm going to use the formulas we had before. So mu of x plus y, that's mu of x plus mu of y. So that's 153 plus 165 is 318. And sigma of x plus y is the square root of sigma squared. So that's 17 squared plus 25 squared. So this will give you approximately 30.2. Okay, this is for the next part of the problem. Okay, so we have the 300 minus the mean over the standard deviation. So we get the probability that z is greater than negative 0.5954. And again, on your calculator, you can do normal CDF, like negative 0.5954, comma, large number. And if your calculator requires it, you can put the mu and mean of 0, standard deviation of 1 for the standard normal distribution. So we get 0.72. Okay. All right. This makes sense. Why, if the mean is 318, it makes sense that the sum of their heights, weights should be more than 300, and the probability is 72%. Okay. Another example. Say you want the probability that x is greater than y. Okay. So we can kind of flip this around. That's the same as saying probability that x minus y is greater than 0. The reason I want to do this is so that we can use our formulas. So back to here then, mu of x minus y is mu of x minus mu of y. Okay. So 153 minus 165, that's negative 12. And sigma x minus y, that's the same as sigma of x plus y, all right? Because you're doing exactly the same formula, whether it's a plus or a minus. You know, put a star here. Okay, that's still 30.232. All right, so we get the probability z is greater than 0 minus negative 12 over 30.232. So that's probability z is greater than 0.3969, which is about 0.346. Okay, and it makes sense why this probability should be less than a half. I mean, if the mean for x is less than the mean for y, you kind of think that x should not be greater than y. Okay, next one. Now this you have to be careful of this. Oops. If I say what's mu of 2x, okay, that's just 2 times mu of x, right, which is 306. If I had the variance of 2x from the formula we had before, that's 2 squared times the variance for x, which is 4 times 17 squared, which is 1156. Now you be careful. You cannot say that 2x equals x plus x. You cannot say that the variance of 2x is the variance of x plus the variance of x. The reason is because these two things are not independent. Once you get a value for x here, since this is exactly the same thing, they're obviously not independent, okay? So you cannot do that. So just be careful, 2 stars here, okay? Because these x values are the same and they're not independent, you cannot do that, all right? Well, this will make more sense when we see problems related to it. Okay, so briefly, I'm going to just derive a couple formulas here. Let me write the formulas down first, and then the rest is a proof here. So if x is a binomial random variable, okay, say there are n trials, probability of success is p, okay, then we're going to come up with these formulas. The mean for x is going to be np, okay, and standard deviation is going to be the square root of npq. Okay, before I get into any of this stuff, for example, suppose you flip like the problem we had before. The probability of getting heads when you flip a coin is 0.3. If you flip the coin 3 times, we ended up with 0.9, and that was 3 times 0.3 is 0.9. Okay, so I'll just go through this quickly. If you can follow this, great. Otherwise, this is the main thing. We need these formulas here. 3 stars. Okay, so suppose you flip a coin one time. Probability of heads is P. And here's my distribution table, looks like this. Okay. This is it's hard to read. That's probability of getting one head is P, then getting no heads, that's a 1 minus P. So 1 minus P, I'm just calling Q here. Okay. So to get mu of X, we use this formula we had before. We took the sum of the xi's times the pi's. So that's 0 times q plus 1 times p, which is p. Okay. Sigma squared, here's the formula we had for sigma squared. Notice the mu we got was p. So we got 0 minus p squared times the probability, which is q, plus 1 minus p squared times the probability, which is p. So that equals p squared q plus 1 minus p is q. So this is q squared p. I can factor out a pq from each of these. I'm left with q plus p. But notice that q plus p equals 1. So this is pq. So that's if you're flipping one coin, the standard deviation is pq. Okay, now suppose you're flipping n coins. So let's look at this random variable x as x1 plus x2 plus x3 up to xn, where xi is how many heads you get on the first flip, which can be either 0 or 1. X2 is how many heads you get on the second flip, and so forth. So mu sub x from the formula we had before is mu of x1 plus mu of x2 plus mu of x3 and so forth. Since for each of these, the mu was p, we get p plus p and so forth. We have n of these, So this equals np. That's what we got up here. All right. And to get the standard deviation, first we look at the variance of x, would be the variance for x1 plus the variance for x2 and so forth. For each one of these, we had the variance was PQ, okay? Yep. So we get PQ plus PQ and so forth. So we have n of these. So the variance is npq. So the standard deviation is the square root of npq. All right. So here we go again, 3 stars. Remember this. Now you might wonder, why are we so interested in this? This is what we'll look at in a minute, is sometimes if we can approximate a binomial distribution by a normal distribution. Before we had calculators, people used to do that a lot more. So let's take a look here. Okay, I'll give you an example first, and I can give you the rationale behind it. Okay, I said note example, page 401. Yeah. Let me show you that first, actually, because I have it on my paper. Okay. So let's look at 3 distributions here. Okay, so suppose I'm flipping a coin 20 times, all right? And the different lists here are for different probabilities. So for this first one, is the probability of getting a heads is 0.1, okay? On my calculator, again, to get all these probabilities here, so for example, to get the probability that you get 0 heads, that was 20 C 0, 0.1 to the 0, and then 1 minus 0.1 is 0.9 to the 20 minus 0, and so forth. That's how I get all these numbers here. So what I did here, I'll show you on my calculator. So I got all these probabilities, and this is what my first distribution looks like. Oops, that's not it. Let me show you the first one. Okay, first one looks like this. All right. Yeah, notice here, you'd expect it to be skewed to the right. Most of the probability is over on this side, and that's because you're not going to probably get many heads because the probability of getting heads is just 0.1. So notice how that's skewed here. Let's look at the second graph. Okay, turn that one on. So this one has p equals 0.3. And what do you notice? Notice here, this is still kind of skewed here. I mean, this is almost 0 over here, but it looks like a lot more normal than the first one was. And let's turn this one off. Let's look at the third one. Oops. Ah, shoot. Why did I do that? I turned them all on. Anyway, here's the third one over here, right? See, this looks a lot more normal, right? It's centered about where it should be, right? It doesn't look skewed, okay? And let me show you this cool site I found. I just kind of Googled it. Let me show you that. I just wanted to show you because it's interesting. One second here. Where is that? Oh, here we go. You can play around with this. This is on Wolfram Alpha. Wolfram is something you're going to be using in college probably because you can do lots of math and do cheats with calculus and stuff by using Wolfram Alpha. Anyway, I just want to show you. Let's look at this first one where I had P was 0.1. Okay, this isn't going to be very exact here. What's wrong here? Yeah, shoot, this worked before. I want to have the P to be 0.1 and N to be like 20 or something. Ah, shoot, doesn't work. It worked a few minutes ago. I don't want to waste my time right now though. See if I can get, why does this work? Let me refresh it. See if it works. Oh, you guys see what's happening there, kind of. Okay. I'm just waiting till this loads up here. All right, now let's see if this works. Okay, I want to make P small. Like here, P equals 0.07. If N is small, then no way does that look normal. But let's see what happens here. If I increase the number of trials here, even if that P is really small, it's starting to look more normal. Okay, now let's see what happens if you make the P bigger. Ah, look at that. Especially if P is like close to 0.5, even if N is small, it looks approximately normal. Okay, now what that means for us is um, back to this example. All right. I'll just summarize it here. In general, if n times p is greater than 10, okay, so like your average number of successes is greater than 10, and n times q is also greater than 10, your average number of failures is also greater than 10, okay? This is called the large counts condition. Then we can approximate the binomial distribution by a normal distribution. Let's give this 3 stars. Okay. So here's the example. Oh yeah, also just one more minor, well, not minor, but say you have a population with 20 things in it, right? You have like some red balls and some blue balls. Well, if you pick a red ball and you keep it, the probability that the next one's going to be red changes. Okay. So to be truly binomial, you would have to put the ball back each time. Okay. However, if you're picking people like from the population to poll, you're going to pick, let's say, one person out of thousands, right? Technically, that's X would not be a binomial random variable because the probability would change each time. However, since the population is so big, the probability just changes minutely each time. So for all practical purposes, it is binomial. So when we remove without replacing, X is almost binomial because the probabilities change each time, but slightly, okay? So in order for this to happen, we want to make sure our sample size is not too big, right? If we take a sample of 100 people from 50 million, that's fine. The probability doesn't change much each time. However, if we took a sample of 100 people from 1,000, that's a different story, or 100 people from 200 for sure. So this is called the 10% condition. We can use the binomial if n, our sample size, is less than or equal to 1/10 of big N, which is the population size. Okay, so if we're doing things without replacing, we can still use the binomial if this condition is met. Okay, so looking at binomial distributions again, sometimes they look nearly normal. So we can approximate as long as this condition is met. So here's an example. Let's suppose that Eleanor, God forbid, guesses on 100-question multiple choice test with 4 choices for each answer. And let X equal number of correct answers she gets. Okay? Now this one actually is binomial, right? Because each time the probability is exactly 0.25 that she gets it correct. The guesses are independent of each other, okay? And the 2 choices, correct or not correct. So I want to find the probability that she gets at least 30 correct, okay? So probability X is greater than or equal to 30. I'm going to use my calculator for this one. That'd be 1 minus the probability that X is less than 30. And if it's less than 30, that means it's less than or equal to 29. And again, I wanted to change this around so I could use the binomial CDF on the calculator. So it's 1 minus binomial CDF, 100, comma, 0.25, comma, 29, and I get 0.14954, which is an exact answer. Now, this binomial distribution, if you draw it out, is we can check here, n times p, 100 times 0.25 is 25, that's greater than 10. And n times q, 100 times 0.75, that's greater than 10. So we can use a binomial approximation, a normal approximation, sorry. So if I want the probability that x is greater than or equal to 30, okay, notice that the mean is 25, which is NP, which is 100 times 0.25. That's where that comes from. To get the standard deviation, that was the square root of NPQ, 4.33. That would give me the probability that Z is greater than 1.1547, which is about 0.124. That's the approximation. It's not real accurate though, right? Now, this is not in the syllabus, but if you want to actually make it more accurate, if you want x to be greater than or equal to 30 by rounding, you could have the probability that x is greater than 29.5. So let me figure out the z-score for that. 29.5 minus 25 divided by 4.33. That gives me a z-score of about 1.039. And that is that gives me 0.1494. See? So this is actually much more accurate. And I mean, you are allowed to do this on the AP exam, but if you just do it like this, that's fine. Now, you're probably asking, well, why bother to even do this if this gives you the exact answer? One reason is suppose you're stranded on a desert island and you don't have your calculator. However, you do have your stat book with your tables in it. You could do this with the tables. And the second thing is before calculators were invented, this is how they did it. All right. Okay, next time what we're going to do is we're going to do a few loose ends with geometric distributions, and then we're going to go into what's called sampling distributions. We'll look at what if you take a sample of 100 people from a population and get the average, what's the mean and standard deviation of that, and is that normally distributed, and what can we do with it? But that's for next time. So I'll see you later. Hope to see you in person soon.